Our next presenter will be György Pirok, talking about Metabolizer and used for P450 first pass metabolism metabolite prediction.
Hi, I think it's proper to say good afternoon now, which is good because the lunch is just 2 presentations away. I would like to speak about a new product which is called Metabolizer. The original title of the presentation was quite ugly. It's a prediction of xenobiotic metabolites, which xenos means in Greece a stranger or foreign. Xenobiotics, according to Wikipedia, are compounds in organs which are not supposed to be there and not produced, or are in higher concentrations than normal. We tested our metabolic system yesterday at the Széchenyi bathhouse with some alcohol, which is in that concentration, might not be normal, or the sweeteners of the soft drinks, or the ingredients of the food what we digested. These compounds, the organisms try to get rid of these foreign compounds. And this progress happens in all parts of the human body, but the main and most important center of that is the liver. And there are various enzymes competing with each other to transform these foreign molecules are present, but the most important one is the Cytochrome P450 family. These compounds, and you may see here in the center, often contain a hem, which can oxidize the compounds. This is a progress to make these foreign compounds water soluble, so you can excrete it. Okay, alcohol and other foreign compounds are also important, but from our sense now, the most common molecules we face with are drugs. And here is an image from a publication with a compound which were transformed to many metabolites. Actually, there could be 1,000 metabolites created from a single compound. There are lots of biotransformations can take place in several places, and they follow follow each other, so it can be a combinatorial explosion. However, experimentally, we detect only some of them. These are the most important ones. Here we have some biotransformations are oxidations, like N-oxidation, cleavage of a methyl here, then the oxidation of this methyl here to carboxylic acid. And some others are called phase 2 metabolic biotransformations, which involve aggregations, for example, glucuronidation. So we designed a tool which tried to enumerate the metabolites of the chemicals like drugs, and must-have goal was to find experimental metabolites, all of the experimentally detected metabolites, even if there are many others created by the software, but these compounds should be there. And no structural errors, those would mean incorrectly defined transformations. We should identify at least one major metabolite. So identify the major ones as well. So not just a blown up pharmacy, but select those which are likely to be detected experimentally. And nice to have feature, we planned to identify most of the, or the majority of the experimental metabolites. And certainly we knew that it's impossible to predict perfectly. So this was never a goal. We started with collecting information from the literature, from collective books, and some articles and papers dealing with metabolism. And we classified these examples from the literature into 159 generic classes, generic biotransformations. This number may change in the future. These are classified mechanistically, and I just would like to highlight that these biotransformations compete with each other to digest the compound. So our model is based on this competition. So imagine, this is a simple model. Imagine a hill with a huge water tank on the top, which the water is the substrate. And pipes go down from that water tank to barrels, and the water can flow through some barrels or can accumulate in those barrels. So, but which are the major metabolites? What do we call a major metabolite? Of course, the one with the highest concentration detected. But what about the one which is almost in as high concentration as the top one, or above 10%? So there is no strict threshold for calling something major. Actually, during the prediction, we just didn't use this majority. We just have an order of the likelihood for the metabolites. But I will use the word major in this context throughout the presentation. So the key of the likelihood prediction is the model that we try to figure out the thickness of the pipes. So the colors here, the arrows here represent biotransformation. So here we have the substrate, and these barrels are the metabolites. And the green color here in this model means a fast biotransformation. The red one is a slow one. So you can see that, for example, this metabolite is produced quickly and consumed slowly on this way, but on another ways consumed quickly as well. So it's probably it doesn't accumulate. But the other one, which is flagged with this likely label, is produced quickly and consumed slowly. So these colors represent the thickness, which is the formation rate. Production is the amount of the material going through a way. So if after this red, very thick, very thin pipe, we have a fast reaction, it doesn't matter because there is no material there. So it will be a low concentration, even if it's quickly transformed together. So we need to calculate the production. And finally, the most important one, the accumulation. So we consider the major metabolite or the likely metabolite, those barrels where the water level increase, so which are quickly produced, slowly consumed or degraded. But the key is how do we calculate the slow or fast biotransformations. So we knew from the beginning that there is no golden calculator plugin for that. We could calculate or predict some radical oxidizations in the Cytochrome P450, but there are many other transformations present, and we have no calculation. The other approach we consider to collect data from the literature. We collaborated with other companies, such as Aureus Pharma in that, but it turned out quickly that everyone measured the KM and Vmax values of biotransformations, which are the same class, just few types, with different protocols, often contradicting results. So we couldn't cover this metabolic space or biotransformation space by an interpolation based on the literature kinetic measurements. So what we did, that we collected we don't need kinetics, we just have known drugs and their metabolites. And we trained the system to the ranks of these reactions, the priorities of this biotransformation in a way to reproduce the experimental metabolites in the best way. So we built internally a random evolutionary optimization tool, and it's nicely reproduced many of the experimental results. So here is a library ranked. So some biotransformation are more dominant than others. So it helps us to create a relative reaction rate for these biotransformations. And let me start here a little demo of our desktop application, starting in a video player. And here we can see Metabolizer desktop application, which includes a library. This library is designed by us. It's a human phase 1 xenobiotic biotransformation library. So if you download Metabolizer, you are able to use this directly to predict human metabolites, phase 1 metabolites. It contains these 159 biotransformations I mentioned, and first example for each from the literature, just to illustrate what this biotransformation does. But if you want, you can load your own library. So it's possible to predict mammal, bacterial, mice, or other biotransformations, but we only provide this human library first. The actual biotransformation, the actual prediction starts with drawing your molecule or just importing with a common name, how I did. The same compound, what was shown on one of the first slides from the literature, it's olanzapine. And actually, it's a root of a metabolic tree. You can manually explore the metabolic space by opening the tree nodes. And each time, all of the possible metabolites defined by these generic biotransformations are calculated and produced. You can see here, if we select the compound, the transformation at the bottom, how it was produced. This was produced by benzylic hydroxylation. The other one is N-dealkylation. And there are some small molecules as well, which is the dealkylation's is the byproduct of the dealkylation step. And we have many biotransformations here. If you don't want these small fragments, for example, or you consider one prediction silly, you can just exclude a metabolite and hide the metabolite from the tree. So you can manually interact with the tool and overjudge the prediction what we made. But certainly, if you open another child level, another generation, the same compound can appear there. So there is a better way to create a blacklist of molecules that you don't want to be in the metabolic tree. It's in the settings menu where there are various conditions, and one is the exclude condition, where you can define a chemical terms expression. Here's just a basic one to exclude all compounds which have less than 7 atoms. So now we reset the metabolism and open the first generation of the metabolites again. It's re-enumerated. And we will see that no formaldehyde is present. OK, this is one way to work with Metabolizer. It's this manual way. But there are automatic ways which can do multi-step metabolism, and there is always a step limit. How many generations do you want to enumerate? We don't want to go to carbon dioxide and water. And there are two automatic enumeration modes. One is exhaustive, so all metabolites and the metabolites of metabolites are enumerated. So it can be dangerous to create a combinatorial explosion. But there is another one, which is we call fast enumeration. And in this fast enumeration mode, we just don't deal with the minor pathways. So we do calculation during the enumeration to filter out those pathways which are not likely. And we have a much smaller list of metabolites now because we did this fast enumeration. But these contain the most significant metabolites and the routes to these metabolites. So There is another page in this application which is called Flow View. It contains the metabolites sorted according to their likelihood. The first one is the most likely. So here we had an alkylation and oxidation to carboxylic acid on the side. And some information also pops up about the likelihood and some of these so-called indicators which characterize the majority of this biotransformation. And if you see, we find the N-oxidized metabolite as well, and its derivatives, and some others. These colors, they mean the likely, probable, and less likely metabolites. Okay, there is one feature, of course, that you can save these metabolites and save the metabolic tree to a file, and it's not a proprietary format. It's we could manage to have it in an SD file or Marvin file as well, so you can import it into the metabolites into other tools. I think that's the end of the demo. We did the test. I don't call it validation because we didn't use fully independent training and validation sets. So it was just a test because it was partially independent. We collected 110 drugs from the literature and then 826 experimental metabolites. We enumerated more than 300,000 metabolites in 4 generations. So about 1,000 metabolites for each substrate. And we were happy because there were no missing experimental metabolite in this huge set. So we had the biotransformations, at least for this set of substrates, no structural errors. We identified at least one major metabolite correctly for 95% of the substrates. And here is a little table showing that how many actual experimental metabolites were identified in the top 10 hits for each of the substrates. So more than half of the experimental metabolites were predicted correctly. So in summary, we have a desktop application for scientists. We also completed an API for integrators, so it is possible to add this functionality to your sophisticated advanced applications. We also have a command line tool which supports batch conversion, and the command line tools already can identify the metabolic, the most risky sites for which can cause metabolic instability. And we provide the human phase 1 library, and we continue to work on it. But that's replaceable with your own libraries if you want. And this is just a beginning. We have lots of ideas how to continue this work, how to make more useful applications on the basis of this new engine. But what we will do, it greatly depends on your feedback. So try it, please try it. Tell us why it's, what is your opinion and how to go further. We have lots of open doors, and we want to decide where to enter according to your feedback. Thank you very much. And my colleagues who helped me to work in these products here. Thank you.
Very nice presentation. The issue of experimentally confirmed metabolites. In my experience, the linkages between precursors and metabolites in public databases is close to 0. And the other thing is, so I'm surprised how many metabolites you could get out of the literature at all. Well, there's obviously a lot there. So it's obviously a very essential conjunction for you if you could either make this database of linkages from the public data, both as a benchmark for you, and of course that you have a obviously you can arrange a linkage between what you start with and a database linked across for the metabolites. A quick other question is, so do you think, are you seeing from the experimental literature most things appear to be accounted for by the P450s rather than adding in the glucuronidase and the glutathione transferases?
I think I understand the first part of the questions clearly. You found the Achilles point of this work, that it was very difficult to find, at least, especially human biotransformation data in the literature. Actually, what we used was the Hawkins collective book, but you had to be very careful what you include in this library, because there were mistakes in the book, but you could recognize it. And those publications often mention human, rat, even goldfish together, and sometimes it's not clear which metabolite belongs to which kind of animal. So in those cases, I just ignored those publications. And there is another, the Drug Metabolism and Disposition journal has many publications about metabolic pathways and xenobiotics, often with assumed pathways. So it's a kind of expert system. This library is an expert system. You have to judge what you involve, and you have to be very suspicious if something is an outlier. One nice example was when I had about 50 examples for a biotransformation, and one of them was an outlier. It just didn't produce the same compound. The region was different. And finally, I realized that it was accidentally a mice metabolite, which was nice because the system just dropped it out. It was an outlier. But that's a problem. And so just ignore those publications which seem not to be reliable.